Hi everyone, this is Martin Shkreli. Here to go through chapter 12 of the Zumdahl and Zumdahl General Chemistry 9th edition textbook. These are pages 552 to 602. The chapter is called Chemical Kinetics. It also could and should be called reaction rates or just reactions. Chemistry is all about reactions. This chapter is specifically about reactions. With the way I look at reactions, and again, we're doing this course with a perspective on medicinal chemistry, and pharmaceutical sciences as the final kind of endpoint, there are sort of two kinds of chemistry that people practice. There's the practical industrial chemistry, which deals with creating molecules. And this chapter has everything to do with that, actually synthesizing different materials and sometimes pharmaceuticals or cosmetic products or whatever it might be at large scales. This chapter is really dedicated to that kind of science. The kind of science I'm focused on is drug discovery and drug development, which really doesn't spend a lot of time thinking about synthesis of pharmaceuticals. I'll give you an example. If you're a drug designer and you decided that you wanted to make a cholesterol-lowering medicine, and this was the exact molecular structure that you like, that this right here on this benzene ring, there should be a fluorine, and not an iodine, or not a bromine, or not a chlorine, and not an ethyl or methyl group, but just this is the exact structure that you need to create a great cholesterol-lowering medicine. Well, that's the drug discoverer, drug designer's job. Then the method of actually synthesizing thousands of kilograms of this exact molecule, that is done by the synthesis groups generally, synthetic chemists, outsourced chemists, and industrial chemists, and that's their job, and it's an important job. And there's no doubt that a great career in chemistry can be done just by creating molecules and sometimes finding faster and novel synthesis routes to making, whether it be medicine or plastics or things like that, is very, very important. So synthesis is at the heart of chemistry. We're going to learn all about different synthesis methods and named reactions in organic chemistry, but for now we're going to learn some basics about reactions. One of the things I wanted to get out of the way is spontaneity. Spontaneity is a concept that a reaction has an inherent tendency to occur. It doesn't say anything about the speed of reaction, though. So if you look at this reaction, two diatomic hydrogen gas molecules will react with one diatomic oxygen gas molecule to create two molecules of water. And that's a spontaneous reaction, but it is very slow and it doesn't occur to any appreciable extent. Reaction rates tell us about the speed of reactions like this one. And we're going to study reaction rates throughout this chapter. And it's going to be very mathematical. I spent a lot of time preparing this lesson because I toyed with the idea of skipping it, but then I decided it was just far too important for us to skip. And one of the reasons I wanted to skip it, it's a very mathematical chapter. You have to understand what logarithms are and have to be relatively facile with them to execute this chapter. A little basic understanding of calculus would also help, but isn't required. So if you don't understand what logarithms are, I suggest that you pause now, review logarithms, which are actually pretty simple, and come back to this course after you understand logarithms. So in any event, reaction rates is what industrial and practical chemistry is all about. And studying these rates, we'll sometimes call it chemical kinetics, but I'll just call it reactions or reaction rates. So let's talk about one specific reaction. Here we have two molecules of nitrogen dioxide that decompose into two molecules of nitric oxide and diatomic oxygen gas. Nitrogen dioxide, if you're not familiar with it, it's a little bit like carbon dioxide, except instead of a carbon, it's a nitrogen, and it's a brownish gas normally. So let's say we had a flask of this brownish gas, and it was at 300 degrees Celsius, so it was pretty high temperature. And we can watch in this table what happens to the reactant. In this case, there's a single reactant. It's just nitrogen dioxide, and it's just sitting there decomposing into these two products. And you can see that if we start with 0.01 moles per liter, depending how big our flask is, it could be a liter flask or 10 liter or 1,000 liters, but that's the concentration. It's 0.01 moles per liter. And you can see by 400 seconds, this is time in seconds, that that almost all of it's gone by 400 seconds, which is about, 7 minutes or so. And you can see that it's being replaced with nitric and oxygen, which have a concentration of 0. There's none of this in the flask at the start of the reaction. But once it starts decomposing, it very quickly gets converted into these two species. And now you could see exactly what happens when it's graphed. You can see that the nitrogen dioxide starts off at 0.01 moles per liter, and then by 400 seconds it's gone. And you can see it's being replaced by nitric oxide and by oxygen gas. And what we're going to study is how exactly these rates occur. You can see it's going down very fast at the beginning, and then it starts to slow down, and it slows down even further. So the rate itself seems to be changing. If the rate was the same throughout, it would look like this. But it doesn't. It has different rates at different times. The average rate for this duration looks like that. For this duration from here to here, it looks like that, and etc. And now the same applies to the products of the reaction. If we look at nitric, it seems to slow down as well. And we're going to talk all about why in this chapter. One of the things we have to understand is, what is a rate? And I stumbled on this earlier. I'm not much of a driver, but I will say that one of the easiest ways to understand rates is to think about miles per hour. So in essence, what we try to do when we have a rate is we have the delta of something, and we divide by the delta of time elapsed. That's what a rate is. So it could be the delta of the amount of a product or reactant, or it could be the delta of something like distance. So if we have point A and point B is 100 miles, I don't know if that's, let's see, maybe the Brooklyn to the Bronx is 100 miles, something like that. Maybe the tip of Manhattan to the bottom of Manhattan. Is that 100 miles? I don't know. Probably more than that. Maybe Westchester to Brooklyn, or Stamford, Connecticut to Brooklyn is about 100 miles. So anyway, if you drove from there and back, or there from Brooklyn to Stamford in 2.5 hours, you'd be going about 40 miles an hour, because the distance delta is 100 miles. So you go from mile 0 to mile 100, and the amount of time is 2.5 hours. So if you divide the change in distance over the change in time, you get 40 miles per hour. And someone else maybe did it in 2 hours, the same equation applies, and it's 50 miles per hour. So the reaction rate is the same thing. We're going to define the change in a concentration of a reactant or a product. I'm going to call that delta A, whatever the A could be. It could be nitrogen dioxide, it could be oxygen, it could be nitric oxide, and then the change in time. The change in time. So let's look. What is the average rate of change for the first 50 seconds of nitrogen dioxide? Well, that's pretty easy. It's going to be change in A, and then also the change in time. Well, the change in time is easy. T2 and T1 are 50 seconds and 0 seconds. So the change is 50 seconds. Now, the concentration at T2 and T1 is a little trickier. You have to look at the table. At T2 is 50 seconds, so the concentration is 0.0079. And the T1 is 0 seconds, so the concentration is 0.0100. And if you take the answer, the change would be the difference between these two, which is negative 0.0021 moles per liter. And if you divide that over 50 seconds, we get our answer, which is this long number, 0.000042 moles per liter per second. Or we could just say negative 4.2 times 10 to the negative fifth moles per liter per second. So this is the rate for the first 50 seconds. And if you look and you draw a line that represents those first 50 seconds, you can see that the rate looks like that. But wait a second, if you look at the next 50 seconds, the rate appears to be slower. And then if you look at the next 50 seconds after that, it's even slower. So it seems to be slowing down with time. And we're going to study why exactly that happens. But the other thing we have to understand is, how do we describe a rate that slows down over time? And this is a really tricky concept. It's called instantaneous rates of change. Instantaneous rates of change is a concept that basically is what calculus is all about. So if you learn a little bit of calculus, this will all be very familiar to you. And what I just drew is called a tangent line. T-A-N-G-E-N-T, tangent line. And so if we think about that tangent line, the slope of that tangent line will tell us what the instantaneous rate of change is. It's always funny to me that if you look at your speedometer when you're driving, it'll say 60 miles an hour, let's say. If it's me, it'll say 100 miles an hour. And the problem is that you don't know that you're actually going 100 miles per hour, because you're not going to drive at that speed for an hour. You may shift even so slightly to 90 miles an hour or 70 miles an hour, and that would change your rate of speed. So how can you measure speed over very short distances? That's one of the key problems of calculus, and we come up with this idea of instantaneous rates of change. So calculating the slope of these adjacent tangent lines, which sort of means that they're touching the curve, based on where they are, tells us what the instantaneous rate of change is, or the speed or rate at that second, at that exact moment. So what's interesting about this reaction is that whenever we observe that rate of change, say let's do it for this first 50 seconds, it looks like this. It's a pretty steep slope, as you can see. What's really fascinating is the other the product of this reaction. That's the reactant. The product of this reaction, one of the products, has the same slope in the other direction. And you can tell it's the same slope because these, when they intersect, they form 90-degree angles. So the slope, this is decomposing, nitrogen dioxide is decomposing as fast as nitric oxide is being created. Now for the oxygen species, this is fascinating. It actually mathematically turns out to be half as much. It turns out to be about half as much as these rates. So that's a pretty interesting phenomenon. And we're going to explain why that occurs in a second. We delete all these lines so you don't get distracted by them. Okay, so those slopes are really interesting. Why do they occur? Well, the rest of the book will be a little bit about that. The rest of this chapter, I will say. One of the reasons is that if you look at this reaction, you can see that 2 molecules of nitrogen dioxide are being created, 2 molecules of nitric are being created, but only 1 molecule of oxygen gas is being created. And that's really the reason why. It's half of the speed. All right, let's go to 12.2. One of the things that's really important to understand is that rate laws are what we describe, how we describe these rates. They follow these laws. There's a reason why this seems to slow down over time. There's a reason why this is half of that, and we're going to describe those. But before we do that, one of the things I want you to keep in mind is that these reactions are reversible. If you look at the decomposition of nitrogen dioxide, you can see it's being decomposed into nitric oxide and oxygen gas, but you can also see that the nitrogen oxide and oxygen gas can reform to create nitrogen dioxide. So it's a reverse reaction, and we call the first one the forward reaction. So the products can actually reform into the original reactant. That's pretty cool if you think about it. And so we're going to tend to avoid reactions like this because one of the things that is complicated about that is it makes it hard to measure this, because if nitrogen oxide and oxygen gas are reforming into nitrogen dioxide, this blue line should eventually go back up. And so we're going to think about that in chapter 13, the next lesson, when we talk about things like equilibrium. So for this chapter, we're going to ignore reactions that have that dynamic. So we're going to assume that when nitrogen dioxide decomposes, that these products actually escape, and they don't become products themselves or reactants themselves to go back to the original product. So anyway, let's talk about the rate law. So the rate law is the rate of the reaction. And the rate of the reaction depends on the concentration of the reactant. If you think about that, the more concentration there is of the reactant, the faster it'll decompose in this case, the faster it'll react. And the less there is, the slower it will react or decompose. And so reaction rates depend on concentration. And so if we look at the rate law format, it looks something like this. There's a letter K, which we know means constant. In this case, it's the rate constant, which is often what we're trying to solve for. Then you have the species, which we can call A, and A can be anything. In this case, it's NO2, but it could be anything. And then it's raised to a power, and that power N is called the order of the reaction. And we'll see how all of this works in a minute, but we know that we have to experiment to determine these values. We can't just guess from the reaction itself. Okay, so we also know that the rate can be determined by calculating the slope. So what's fascinating here is that it turns out that these two things are equal. Turns out that these two things are equal. And so when we look at rate laws that express the reaction rate as a function of concentration, we would call those differential rate laws. And there's a different kind of rate law, and we refer to that as the integrated rate law, and that describes the concentration as a function of time. So sometimes we'll want to know what the concentration will be at any given time, and sometimes we'll want to know what the reaction rate is given a certain concentration. And what's interesting is we can use math, and especially calculus, if you're familiar with differentiation and integration, they're opposite procedures. We can use those to derive one from another. So let's take a look at 12.3. We're going to try to determine a rate law. One of the reactions that we're going to study in this chapter frequently is this dinitrogen pentoxide. And this is also a species that decomposes. So here we have two molecules of dinitrogen pentoxide, N2O5. And you can see that it decomposes on its own to nitrogen dioxide and oxygen gas. It's kind of funny because nitrogen dioxide we know decomposes to nitric oxide. So this will decompose even more. But in any event, when we look at this reaction, I've graphed it here, and you can see that the rate of the reaction at this level and at this level are very different. You can see the hypotenuse of the triangle, for instance, is much longer here, even though the heights are about the same. And the reason this is interesting is basically that at 0.9 molar, the reaction rate is double that of 0.45 molar, which is really fascinating, because what that ends up telling us is that when the concentration of N2O5 is halved, what ends up happening is that the rate is also halved, which is a really fascinating finding, really. If we do all those calculations, we see that the rate here, it's going down at 5.4 times 10 to the negative fourth moles per liter per second, and here it's 2.7. That's exactly half. So at the end of the day, the reaction rate depends on the concentration to the first power. So we call that a first order reaction because the exponent of the rate law is 1. And we're going to use that a few times going forward. So how do we do this in real life? Well, what we do is there's a method we like to call the method of initial rates, and I'll show you this experiment here. What you do is you do several experiments, and you want to measure the rate of reaction immediately, right when you start the experiment, over the first few seconds. And you can see that we call that the initial rate. And if you do several experiments where you vary the concentrations of each of the reactants, you can tell how the rate law is supposed to look like. So in this case, we have ammonium, the ion, and nitrogen dioxide. And so in the first experiment, we have 0.1 molar of ammonium, and we have 0.005 molar nitrogen dioxide. And then we use the same amount of ammonium, and we double the nitrogen dioxide, and we see that the rate has doubled. And in a third experiment, we use the same nitrogen dioxide, except we double the ammonium, and we see that it's doubled yet again. So what does this tell us? Well, we know that the rate law will look something like this. It'll be K, and then the ammonium species to the nth power, and then the nitrogen dioxide species to the m power. So the question is, what are these powers? What are n and m? What are those values? So we have to think that through. So one of the ways we can do that is we can take this rate and divide it by this rate. And what we see is the rate is double. 2.7 times 10 to the negative 7th is double the rate of 1.35 times 10 to the negative 7th. And the reason that that's interesting is we double the concentration of nitrogen dioxide, and so therefore the rate got doubled. So if we look at the rate of the experiment 2 divided by the rate of experiment 1, the value is 2 to the m. Well, 2 to the m equals 2. What is m? Solving for m means 1. 2 to the first power is 2. So the value of m is 1. The value of n is also 1 if you look at experiment 3 versus experiment 2. So now we can actually derive k. What that means is for any concentration of ammonium, the ion, and nitrogen dioxide, we can determine what the rate will be for any specific concentration. So solving for that rate constant k is very important. Here's another interesting problem. I'll call this 12.3c. And this is bromate plus bromine ion plus protons, hydrogen ions, results in 3 diatomic bromine gas and 3 water molecules. And we have the experimental data for this reaction. Again, we use this method of initial rates. We hold all 3 constant at 0.1 molar, then we raise this one, then we raise this one, and then we raise this one. And that way we can determine the rates of each. So if we look at experiment 2 versus experiment 1, everything's being held constant except for the bromate. And you can see when we double the bromate, we double the rate of the reaction. So if we divide reaction rate 2 over reaction rate 1, the answer is 2 to the nth power equals 2. So n must be 1 in this case, or you can just delete it. And if you carry on solving this, the only thing you'll find here is that the hydrogen has to be, if you do the reaction rate of the hydrogen, you'll find that it's 4 times faster, interestingly. So if you look at experiment 1 versus experiment 4, it's actually 4 times faster. So 4 over 1, you have to do it like this. 4 over 1 is equal to, it's 4 times faster. Look at the rate. It's 4 times faster. 32 divided by 8 is 4. But you only doubled the amount of protons. So that's 2. So the rate is 4 equals 2 to the p power. So p must be 2 because 2 squared is 4. It can't be in the first order because 2 to the first power is 2, and we know that it's 4 times faster. You can see it's 4 times faster. 32 divided by 8 is 4. Okay, so we know now that the overall reaction order, which is just the sum of all the orders, is 4, but the rate law, more importantly, is K, bromate, bromine, proton to the second power. And solving for K is really easy. We can just plug in any of the values and then divide those values by both sides to isolate K, and we see the rate is always going to be 8.0 liters per mole per second. And so for any concentrations, we can determine the rate that way, which is really cool. So that's how powerful this method is. And if you're making vats of ammonia or fertilizer or plastic, this stuff is really important. All right, let's go to the integrated rate law. So this is a bit of a different from the differentiated rate law, or the differential rate law, and this is concentration as a function of time. So we know a first order reaction is the one where the rate depends on the concentration of the first power. But if we use calculus to integrate that differential rate formula, we get the logarithm, and this is the natural logarithm, and that's to the 2.718. And I always remembered 718 because it's the Brooklyn area code. So 2.718 is the number E in math. If you don't know much about E in math, it's a very important mathematical concept and constant, and it roughly equals 2.718. It's also sometimes called Euler's number. So if we use logarithms, which are usually in base 10, but in this case, a natural logarithm is in base E, or 2.718, and we take the natural logarithm of some concentration of A, we can find that, or we're looking to get that number, we can find that it's actually equal to the negative of the rate constant multiplied by the time plus the natural logarithm of that concentration at time 0. So this is really powerful stuff. If you think about this, you can see that you can use the rate constant. Once you know K, you can determine the concentration of A at any time at all in the reaction once you know K, which is great. The other thing that's interesting is this is in a linear format. It's in the format of y equals mx plus b, which is pretty cool. So you can graph this linearly. And if this ends up being a linear equation, we know that the reaction is in the first order. So we're going to find that that's pretty neat and useful too. So if we look at the same reaction of dinitrogen pentoxide decomposing, and we graph it, and I'm actually going to do this. I'm going to do this in Excel. I recorded this lesson earlier, and I went through it too quickly, so I'm re-recording it. That's how much I love you guys. And I'm going to show you how to do this in Excel. So the first value at time 0 is 0.1. And so in Excel, you do equals log. I take this number, and I want to convert it into a logarithm, and that's the number. It's negative 2.3, and you can see that's approximately where it is on our graph. And this might be complicated to you. You might say, oh my God, Martin, I understand that the concentration of this mysterious gas is zero point 0.1 moles per liter. I get that. I've listened to your other lessons. I know what moles are. I know that what liters are. But now you're telling me that we're taking that number and we're converting it into this crazy Euler's number logarithm. Well, if you understand logarithms, you know that this isn't as scary as it looks. This is just a different way of writing 0.1. Except we're going to write it as negative 2.3. It's like a different language, the same way French is hard to understand sometimes. So anyway, if we keep converting these, we can convert them as so. So this is 0.0707. Let's do it like this. And I can just copy and paste this thanks to the beauty of Microsoft Excel, my favorite program. And we can see I think there's a typo there. Is that a typo? Could be a typo. Yes. I'm glad you guys caught it. There we go. And you can see this is how I got these numbers. Negative 2.3 all the way down to negative 5, and these are all log transformed for the natural logarithm. And if we graph it, it comes out this really nice looking graph. And this doesn't really look linear, does it? Well, because there's a bend here. Well, the reality is that there's an error that is explainable. And let's see, let's make sure that we got this right. This doesn't look as linear as it could be, does it? I think there's a issue with the time values. So there's 6 values, 2, 3, 4, 5, 6. But the what's neat about it is I think one of these values doesn't belong because it's a shorter period of time, and that's this one. So if you redo it, because that's for 50 seconds, so if you redo it, it's a perfect linear relationship. So these are by seconds. So if you do it, and I had this huge issue when I was doing this, and I realized immediately that if you look at the 50-second value, Excel kind of screws it up. So I eliminated that 50-second value to get the linear relationship, which is nice. So anyway, that's how you do the problem. And so it's perfectly linear here, which means that it's a first order. It's first order in dinitrogen pentoxide. So we know there's a first order reaction. So calculating the slope is going to be very easy. Let me fix this as well. So we can just take any of these values. We can take and what's amazing is we take the log transform value. So we take this value, which is 5 something, 5.0 something, and negative 2.3, and we take the delta, and we see it's negative 2.772 over 400 seconds, means this is the new value of k. And so now with the value of k, what we can do is we know we can calculate the concentration at any time point, at 392 seconds, at 7,000 seconds, any number of seconds, we know exactly how much dinitrogen pentoxide we have. So that's why this is a really cool equation. So the half-life of a first-order reaction is this is also pretty cool. What we find is, and this is actually pretty useful in pharmaceuticals, first, the half-life is the amount of time it takes for anything to deplete by 50%. And we know that when we take a drug, that in our bloodstream it only lasts for a finite amount of time because it's decomposing, it's being metabolized. Also, radioactivity has half-lives. Everything in some way has a half-life. And the way we can derive the half-life is by this cool equation of 0.693 divided by k is the integrated rate law for the half-life of a first-order reaction, which is pretty incredible that all half-lives can be approximated by using this formula for a first-order reaction. And I'm not going to go through the math of why that's the case. Now, if we do a second-order reaction like Ka squared, something that's in the second order for A, we get this cool formula, 1 over A equals KT plus 1 over A at time 0. And we can use this and graph it as a linear, you can see it's a linear equation, and that graphing this with respect to time will give us a parabolic or curved line. So the half-life looks a little like that in terms of this formula. For zero-order rate laws, most reactions won't be zero order, but there are some zero-order reactions, and the rate is just equal to K, which is kind of interesting. If you do the integrated law, this is what it looks like. It's just minus KT. So it was all pretty simple stuff. I'm skipping one page, which stretches over 2 pages, but it's really 1 page of content. And I don't think the book does a great job of explaining it, and I don't think it's a very valuable page, but it talks a little bit about integrated rate laws for reactions with more than one reactant, which most reactions have more than one reactant, and it talks about something called the pseudo first order rate law. So if you want to learn about the pseudo first order rate law, I would encourage you to look somewhere else. The rest of this chapter is a little less math, and we'll go through it like this. So we have nitrogen, our friend nitrogen dioxide again, reacting with carbon monoxide to form nitric oxide plus carbon dioxide. And the rate here we experimentally determined is in the second order. And this reaction is much more complex than it looks, because if you look at the reaction in isolation, you can see that it's just sort of this oxygen flipping over here into this. So the oxygen disappears from the nitrogen species, moves to the carbon species. Turns out it's a lot more complicated than that, where it actually forms this nitrogen trioxide species. And this is an intermediate, which is an important word to learn. This is created and consumed, but it is not a reactant or a product of the reaction. It's an intermediate. And there's some laws for determining the rate laws of these intermediates. And it's through this concept called molecularity, which is the number of species that must collide to produce the reaction. So that's a nice concept, and I would encourage you to study it further if you would like, but it's not terribly important. The rate limiting step is something I think we all have familiarity with. It's the slowest reaction in a reaction process, and that's something that I think is pretty self-explanatory. And so let's move on to modeling chemical kinetics. I'm going to spend a little bit of time here and then we'll be done. In essence, chemical kinetics is somewhat difficult to model in that you have these molecules colliding with each other, and these collisions occur, and to react, to actually have a decomposition, let's say here, of this species, there actually has to be these collisions. If they don't have the collisions, there won't be any reactions. And we all know that the collisions go up, right, with temperature, which makes a lot of sense. Temperature and energy are things we studied earlier, and we kind of understand that the higher the temperature, the more likely these collisions will occur, and the more likely these reactions will occur. And that's why you always get rates increasing with temperature. That's a really important concept. So sometimes, though, when we look at the actual quantitative data, it's a very difficult to sort of reconcile this idea that only a small fraction of these collisions actually produce reactions. So why does that happen? Well, Arrhenius, who was also defined the acid and the base and won the Nobel Prize, really important founder of chemistry, proposed a model to satisfy all these observations, and he called it the activation energy. So there's a threshold required to produce a chemical reaction. The species here doesn't just go and decompose immediately. It actually has to hit a transition state. It has to gain enough energy and overcome this transition state where it'll transition into the products. Now, we all know reactions will only occur if the products have a lower potential energy than the reactants. And that happens here, but it's a little counterintuitive that it actually has to climb up an energy barrier first. And then the energy can go lower, which is kind of interesting. And Arrhenius ended up developing this equation, and I'm not going to go through this in too much detail, but it looks a little like this. It's a natural log of K, or the rate, is equal to negative EA, which is this activation energy, this top threshold, and then it's divided by the universal gas constant, which we know, multiplied by 1 over T, the temperature in Kelvin, plus the logarithm of the concentration. And in essence, we can use this to determine the activation energy, which is somewhat important if we're going to do reactions. So if we look at this, I'm going to show you how to do this. This is dinitrogen pentoxide again. And we have this table. These are the results we got. We know that at this temperature in Celsius, 20 degrees, this is the rate. It's 2.0 times 10 to the negative fifth. So let's plug all that into Excel. The temperature in Celsius is 20, so we know that the temperature in Kelvin is going to be plus 273 degrees, or 293. And we have the values for 20, 30, 40, 50, and 60. So we have the temperatures in Kelvin just by copying and pasting the formula. And then we have K. This gives us K is 2.0 times 10 to the negative fifth. So that's 0.002, right? 1, 2, 3, 4, 5. 2 times 10 to the negative fifth. And here it'll be the same except 73. And here it'll be the same except it's three zeros instead. It's 27. And here it's the same except it's 3 zeros, 91. And here it's 2 zeros and 29. So we can see that the rate goes up with temperature, which makes sense. That makes a lot of sense. But how do we convert this into a log? Well, we know how to do that. We can take the number and we do it by 2718. And here's the log transformed numbers. These are the log transformed numbers. And now what we need to do, though, is they're actually telling us that it has to be 1 over t, 1 over t as well. So let's go back. 1 over t, that's just easy. That's here. 1 divided by t in Kelvin. So this is lnk. So here I put in t, 20, 30, 40, 50, 60. Here I added 273 to this cell, and I just copied and pasted it so it's in every cell. Then they gave us the rates, so I put those in without the scientific notation. I log transformed them using the natural logarithm, Euler's number, and then they asked us in Arrhenius' equation to calculate 1 over t, and we obviously have to use Kelvin. So now that I've got all that, I can actually do this equation. And this equation is pretty complicated, but I'm trying to solve for EA. Here's EA. So I have the log transform value of K, I've got R, I've got T. So let's see if I can do this. Well, taking the slope is simple. So we can take the slope here, and what's complicated though is that y always equals mx plus b, and in this case m is equal to negative a divided by r. And we actually can start to sort of transform this around because m in this case will actually be let's see here, we have m because it's m equals negative a is r, so we rewrite, so EA equals negative r times m. So we multiply r by both sides, we isolate EA. So EA equals r times m, and m we calculated is the slope. And here's how we calculated that. R is always the gas law constant, and that's 8.314. So the activation energy is 1 times 10 to the 5th joules per mole. So this is a pretty complicated equation. The way we calculated slope was we graphed, here's the graph, we graphed this value. So let me show you how we did that. Here's the logarithmic transform values, and this was really complicated. I graphed them, and it turns out that you have to graph them in the opposite direction. So I went into here, and I edited this. Remember, we're graphing it with respect to, it's too large. We're graphing this with respect to a different axis than you might be familiar with. We're graphing with 1 over t, and this is a pretty interesting phenomenon. So we graph it with respect to 1 over t. We actually also want to reverse the direction of of the axis, which is even more complicated. And when we do that, we get this chart. And it's linear, and you can see that it's perfectly accurate. So the slope is easily calculated. You take the delta of two values, divide it by the delta in temperature, or 1 over T in this case, and you get the slope. And of course, we know the gas law constant, so we can solve for activation energy, which is crazy. So that is the finale. Catalysis is the last thing I'll talk about. It's the use of catalysts to speed up reactions. And the interesting thing about speeding up reactions is that the way we do that is we lower the EA, the activation energy required. That's the peak, or F double prime for you calculus people. The peak of this is called the activation energy. So we want to lower that so that these reactions can complete with less energy and more reactions. And we use enzymes in our body because we can't raise the temperature. One of the easiest things to do is to raise the temperature a lot. And we can do that with nitrogen dioxide or dinitrogen pentoxide by going up to thousands of degrees. But in our body, we can't do that. So we have enzymes that biologically do these reactions for us. But catalysts are typically what we use in industrial chemistry. And there's a lot of different kinds of catalysts. There's a homogeneous catalyst and a heterogeneous catalyst. And some of the heterogeneous catalysts use adsorption. That's different from absorption. A sponge absorbs. Adsorption is a collection of substance on the surface of another substance. Something can be adsorbed as well. So anyway, I hope you enjoyed this chapter 12. Chapter 13 will be about equilibrium, and it'll be similar in the way that it's mathematical and detailed and intense. I like this PowerPoint format. It helps me schedule the lectures and prepare for them a little bit better. And I hope to see you next time. Thanks so much.